welcome to the first of 2 tutorials on the subject of Surds. I strongly recommend watching the tutorials on numbers before you study these tutorials, unless you're very familiar with the idea of rational and irrational numbers. So just a brief recap to start with. When we speak of surds, what we're really talking about are numbers such as the square root of 2 or the square root of 3 and so on. These are irrational numbers, as we talked about in the numbers tutorials. Just a brief reminder here, we have the number line, which is the set of all real numbers. We have the integers sitting on that line, both positive integers and negative integers. We have rational numbers, which we colloquially know as fractions, but strictly speaking fractions of integers on this line as well. So for example, here's 1/2, and here's, for example, -4/3. So all fractions of integers can be represented on this line too. There are an infinite number of points on this line which cannot be represented by fractions of integers, by rational numbers. These are the irrational numbers, and the surds, which are square roots, cube roots, various roots of integers, are a significant subset of these irrational numbers. And the subject of this and the next tutorial is just to give you an understanding of how to do arithmetic with these numbers. So, by definition, the square root of 2 is a number which, if squared, gives you 2. And likewise, the square root of 3 is a number which, by definition, if multiplied by itself, gives you 3. We can list some of these square roots. Let me think of the square roots of the following numbers, and I want to go up to probably 16 here. I'll go up to 17, why not? Nice prime number. So the square root of the numbers above are, of course, well, the square root of 1 is 1. The square root of 2 we represent as this symbol, square root of 3. Now the square root of 4, because 4 is a square number, is just the integer 2. Then we have the square root of 5, the square root of 6, the square root of 7, the square root of 8, and then again we come to a square number. Its square root is just an integer, in this case 3. And then we have a spate of surds. Collective noun for surds apparently is a spate. I just made that up. And until we get to the next square number, and then the square root of 16, of course, is just 4, and then so on. So the first thing to realize with the surds is that they are the square root of integers, except those positive integers which are not, which are square numbers. And that's important, as we'll see in later on in this tutorial, is identifying square numbers as factors of the integer within a square root sign. For now, though, let's just ask a very simple question. How do we do arithmetic with these surds? Arithmetic with surds. And in this tutorial, I will just talk about multiplication, and then in the next tutorial I'll talk about addition and subtraction, and also briefly mention division. So it turns out that multiplication with surds is very straightforward. Obviously the square root of a surd, if it's a square root, the square of a surd is just multiplying it by itself, which gives you back an integer. If we look at the multiplication of two surds that are not the same, so the square root of 2 times the square root of 3, then this is nothing other than the square root of 2 times 3, which we can just obviously write as the square root of 6. You might ask, why is that true? And we can just check that very quickly. If we take the square root of 2 times the square root of 3 and multiply it by itself, then we have the square root of 2 appearing twice, and we have the square root of 3 appearing twice, which is 2 times 3, which is 6. And so this number should be the square root of 6, which we indeed see that it is. So generally then, any two surds that you're multiplying together, so for example the square root of 7 times the square root of 11, we just take those integers inside the square root sign under one large square root sign, multiply the integers together, and voila. So very straightforward. What it shows you is that surds like the square root of 6 or the square root of 8 or the square root of 10 can be built up from smaller surds, whereas surds like root 5 or root 7 or root 11 are in a sense unique and cannot be built up of smaller objects. These numbers 5, 7, 11, 13 and so on are of course the prime numbers, numbers which do not have any factors apart from themselves and 1. Very important is the idea that we can do this backwards, so we can take the square root of 6 and we can decompose it into the square root of 2 times the square root of 3. Likewise, we can take a number such as the square root of 12 and we can break it up into smaller surds. So, for example, we could write this as the square root of 4 times 3. We could then break up the large square root into two smaller ones. You see how here multiplying two individual square roots gives us an overarching square root of the integers, so we can go in reverse. So here these two factors under the square root can be written separately, each with its own square root. And what we see here is that we now have the square root of a square number, and so this is actually 2 times root 3, which we commonly just write as 2 root 3. Just going to shift the paper up so I can just do a couple more examples before I end the tutorial here. So it's very important to be able to spot if there are factors, and particularly if one of the factors is a square number. So for example, if we have the square root of 14, this will have factors, but neither factor will be a square number. So I can write this as the square root of 2 times 7, and then decompose that as root 2 times root 7. And I can't simplify that anymore. On the other hand, if I have a number like, let me just make one up here, 18, I can write the square root of 18 as 2 times 9, and then you see I have one of the factors as a square number. So I would write that as 3 root 2. So quite interesting when one considers multiplying surds and the opposite operation of breaking down surds or decomposing them into smaller factors. If the surd is the square root of a prime number, there is no way to simplify it. If the integer inside the square root has two factors, neither of which are square numbers, then one can at least break it down into two smaller surds. If, however, the integer under the square root, like in these two cases, can be written as a factor, one of which is a square number, then you can have a much greater degree of simplification, and you'll end up with an integer factor of a single surd. And this technique actually is something that the examiners in the Scottish National 5 curriculum and probably other school board curriculums around the world will ask you to have, is identifying the degree to which you can simplify square roots of higher integers. So I hope you found this helpful. In the second part of this topic of surds, I will look at addition, subtraction and division of surds. Okay, thank you very much. I hope it was helpful, and I'll see you next time.